And hello, my AP Calculus friends. We're going to take a look at our example 8 from topic 6.3. We're still right in the middle of this process of finding the exact area under a curve using the idea of an infinite number of rectangles and letting those rectangles approach infinity and summing them up and completing the problem with all of the algebra that's required. It's definitely a challenge. Let's keep pushing through, and maybe there might be a shortcut for this whole process down the road. So we're going to take our look at our limit process version number 2 problem here with example 8. So notice what we've got. The limit process is to be used to find the area between the function y or f of x equal 4 minus x squared, the x-axis, and the pair of vertical lines x equal 1, x equal 2, which really doesn't come into play much since the curve crosses the x-axis at 2. In any event, we want to find the exact area of that shaded gray region. Well, we've done a few of these already, so all of the things that we've done before are still in play, where we find, first of all, the width of our rectangles. And the formula is always going to be your rightmost boundary minus the leftmost boundary, in this case 2 minus 1, and we divide by n, which is the number of rectangles. And so that does simplify to 1 over n. Now, what sometimes is the tricky part for students, finding the length, or we say the height of each of these particular rectangles. We have adopted the fact that we use the function, and this y is every bit the same as f of x, I want you to know, in this particular case. And we have to start at the a value. And it's so unfortunate in this problem that a is something besides 0. It happens, not frequently, but if it does happen, we just have to deal with it. So what that means is that you don't want to start counting your increments of intervals until you get to this place where 1 is, and then you're just going to add stuff to this to figure out where your stopping points are going to be for this setup. Now, as always, we use the width 1 over n, and then the crucial decision. Do you use I for the right endpoint, or do you want to use I minus 1? It's your choice, guys, because you know you're going to get the same answer. If you look very closely at our example 6, you'll see that we investigated that, or I'm sorry, even back before that, in example 5, we investigated that. So you can use either an I here or an I minus 1. Think about that. We want to try I minus 1, don't we? At least one time? Oh, come on. I know you want to do that. No? You're serious? You want to stick with I? Good job. That's what I want you to do. Don't give in to peer pressure. Always use the right endpoint I. It's going to make things so much easier. Now, what I would suggest here is that we go ahead and get a common denominator, which is n plus I over n. I think that makes things a bit easier. And then we can fully immerse this into our function. 4 minus x squared is now 4 minus the quantity n plus I, all divided by n squared. And there we've got it. Our setup is ready to go. So that means that if we find this area, we're going to do nothing but take the limit as n approaches infinity of the summation as I goes from 1 to n. I said many times that you're going to wish that you had a stamp that had this notation on it. Plop! And you can just plop that on your paper whenever you needed it. We have our height here that we talked about. That is an I, by the way. And then all of this is going to be multiplied by our width, which we know is 1 over n. So there we go. So what do we do next? Well, good question. What do we do next? I would think that we probably want to go ahead and square out this n plus 1 over n. So the limit is going to drop straight down. The summation is going to plop straight down. We have a parenthesis, and I tell you what I'm going to do. I'm going to suggest a little something here. Since in about 2 seconds, This n in the denominator is going to become an n squared. I have a proposal to make. How about we give this 4 that same common denominator of n squared? Wouldn't that be just super duper? We could drop down the minus sign, and now n plus I has to be squared. I don't know how much trouble you might be having with that. Sometimes you do have trouble with some of this algebra. It's not a sign of weakness. Just, do whatever it takes to fix those issues. If you have to write this out, that's fine. N times n, of course, is n squared. The middle term is I times n, but take a look. You got 2 of them, don't you? So 2in. And then the last term is I times I, which is, of course, I squared. And let's extend that fraction. So 4 minus n plus 1 over n squared is going to be all of this information that I have here now. And then I would multiply that by 1 over n for the width. And we're well on our way, folks. Our algebra is taking shape. It's a lot of it. All right, for the next step, I am going to suggest that we clean this up a little bit. This thing is a train wreck. This thing is really ugly looking. So what I would suggest is we distribute this negative sign and then combine some like terms. That sounds like a great idea to me. So this numerator would be 4n squared minus n squared, which of course is 3n squared. And then I distribute the minus to the 2in, and I will distribute the minus to the I squared. And now I just have a single n squared there in the bottom. That would be the height simplified. And once again, the width is 1 over n. Each step, we're getting closer and closer. The next thing, let's factor out anything out in front of the summation that does not contain an I. And I can clearly see that 1 over n cubed does not contain I. So we can bring him out in front, 1 over n cubed, and then have our summation acting upon what's left, which would be 3n squared minus 2in minus I squared. Now, I'm not sure if you're thinking this or not, but some students think, well, wait a minute, why didn't you bring out the 3n squared? Because it doesn't have an I. Well, the reason is because we kind of can't. This thing is kind of tied up in a binomial with addition and subtraction. We can really only factor out things that are being multiplied or divided. Now we are going to use our limit properties and some of our limit formulas. So everything else stays the same here at the beginning, but now the summation of 3n squared is going to be the summation of a constant times the upper bound n, and so that's 3n squared times n, which is 3n to the third. Anytime that you have an expression here that doesn't have an I, you basically multiply it by n, and that takes care of it. Next up, we have minus 2 times n, and then the summation formula for I, if you remember, is n times n plus 1 all over 2. That 2n comes out in front because of those two guys. And then we have a subtraction, and then the summation formula for I squared goes a little something like n times n plus 1 times 2n plus 1 all over 6. And we are making more headway each and every step. Boy, this is an understatement. If you can do these problems, then you are definitely, I want you to think about this. Even pause the video, challenge yourself. I'm giving us a break mid-problem because I know you've been working hard. Take a look at this puzzle, think about it, pause the video for about 30 seconds, and then come back and see if you're right. Okay, and we're back. You didn't cheat, did you? You didn't look this up. You didn't Google this, did you? This would be a brain, which means smart, right? Or smarter, if you're talking about an inequality symbol. The summation as I goes from 1 to n divided by n is another way to say average. And of course, this is a bear. So you are smarter than the average bear. It's an old expression from an old cartoon long ago. Now, if I can get rid of this, this would be super duper because you're done. We don't need you anymore. So let's keep working here. So we are pretty much at that stage where if you can take this limit, you're in great shape. Some of you might be able to do this common denominator work in your head and extract the highest powers of n on both the numerator and denominator and then divide their coefficients. More power to you if you can do that. What I suggest for most of my students is that you at least get the common denominator. So I see that 6 is going to be a common denominator among this wide array of fractions here. And so the 3n cubed needs to be multiplied by 6. So did it. This 2n times n, which I'm just going to call that 2n squared. If I multiply that by 3 over 3, I'll have 6n squared times, of course, an n plus 1. And then I don't think this last expression needs a doggone thing because he already has the denominator of 6 that's required. And at this point, I think we're just about there. I think this is going to be our last step of simplification because it seems pretty evident that the denominator is going to be a 6n cubed. So we need to make sure that the numerator also has an n cubed, and I think it's going to because I see 18n cubed minus what would eventually be a 6n cubed minus what would eventually be a 2n cubed. Hopefully you see all that. 18 minus 6 minus 2, that's 10, isn't it? 10n cubed. And when it just comes down to it, anything else that's left in the numerator is not required because everything else in the numerator consists of exponents of n that are less than 3. Right? This 6n squared with a minus that's going to be there. And then all of the inside, outside, last terms of this FOIL is not going to have an impact into our answer. And so once we see that the degree of the tops are both 3, we can divide the coefficients. 10 over 6 is our answer. Of course, we can maybe reduce that to 5 over 3. And you know what? This is our right answer, but this always gives me kind of some inspiration to try something. So would you guys just kind of excuse me for a moment while I work on something? I see that the function was 4 minus x squared, so I'm kind of tempted to do this. And maybe put this little symbol there in front with respect to x, and then use the boundaries 1 to 2. And if I do that to a 4, I get 4x. If I do that to an x squared, I get x cubed over 3. I know you're thinking, where's that all coming from, right? All right, and then let's plug 2 in. 8 minus 8 thirds. Built-in minus, plug in 1. 4 minus 1 third. And if I were to do all this math, 8 minus 4 is 4. Negative 8 thirds plus 1 third. Negative 8 thirds plus 1 third is negative 7 thirds. And that's going to be 21 thirds minus 7 thirds, which is 14 thirds. This kind of gives me the impression that I may have messed this problem up. And I think I don't know how to do math. Let's go back. 4 is the same as 12 thirds. I got my 2 and 1 mixed up. 12 minus 7 is 5 thirds. Boy, that was going to have a much more impactful conclusion if I didn't make that screw up. But there's something to be said about this. And I'm going to keep investigating this and see if maybe this might be a better way to do that same problem. Stay tuned for that. Meanwhile, we're still going to talk a little bit more about the limit process in the future videos. We hope you enjoy this. We hope you stick around for future videos. And as always, thanks for joining.